Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of this lecture is Equations of Change for Non-Isothermal Systems. Before going into the details of equations of change for non-isothermal system and then derivation of respective conservation equations etc., what we do, we are going to have a kind of recapitulation of what we have seen in last two lectures. In last two lectures, we have seen a few basics of continuum hypothesis. Then we also recapitulated transport mechanisms, and out of which we have seen the details of molecular transport mechanism concerned with the momentum transfer, heat transfer and mass transfer. Then we have also seen analogy amongst the momentum transfer, heat transfer and then mass transfer, especially when the transport mechanism is governed by the molecular transport. Then we also seen a few basic details of partial time derivative, total time derivative, and substantial time derivative, and what is the difference amongst these things we have seen with an example of a fish concentration in a river stream. Okay. Then we have also derived the equation of continuity, that is nothing but conservation of mass, and then that we got dou rho by dou t is equals to minus del dot rho v. This equation we have written rectangular coordinates, cylindrical coordinates and spherical coordinates. If the same equation if we write in substantial time derivative form, then capital D rho by dt is equals to minus rho del dot v, that is what we get. Then we also derived the equation of motion, that is nothing but conservation of momentum for a very generalized system irrespective of the nature of the fluid, irrespective of the nature of the flow regime. We have derived the equation of motion, that is nothing but dou by dou t of rho v is equals to minus of del dot rho v minus del p minus del dot tau plus rho g. This is what we have seen. If additional forces or additional terms are also causing momentum transfer, so then those terms should also be added in the right hand side, that is what we have seen. Then the same equation if you write in substantial time derivative form, then we got this rho capital D v by dt is equals to minus del p minus del dot tau plus rho g. This is what we have seen in last two lectures. Now in this lecture we are going to derive equation of change for non-isothermal systems. So that is nothing but conservation of energy, that is what we are going to derive. So now when we talk about the conservation of energy, what we try to include? We try to include all the forms of energy, and then we also include the transport of energy because of all possible mechanism. Plus in addition we also include energy because of any additional work done because of the molecular stresses or because of the external forces like gravity etc., all those terms we include, and then very generalized energy equation we are going to develop. That is what we are going to do in this lecture. Then subsequently what we are going to do, we are going to simplify this equation so that to get a final energy equation in a very simplified form, where we can have this energy equation in the form of temperature. Why in the form of the temperature? Because temperature is a measurable quantity, so then application of energy equation would be more appropriate if you write that energy equation in the form of temperature. So what are the types of different possible energies that may be associated with the system? So we may have the kinetic energy, we may have the potential energy, we may have the internal energy, we may have the work done on the system because of the molecular stresses or because of the external force like gravity etc., or because of the reaction. All those things may be causing some kind of work done on the system, and then that may be including some energy, so that all those terms may be there. Okay. Then like that these different possible energies, let us say reaction energy, or if you have electrical energy associated with the electrical electric gradient, electrical potential gradient etc. If you have the energy associated with the electrical potential gradient etc., those things, different forms of energies are all possible, right? So we are going to see how generalized way we can include most of these terms, if not all. That is what we are going to see. And then this energy may be transporting because of the different mechanism, both by the convective transport mechanism as well as the molecular transport mechanism. So, that is what we are going to have. So, then we are going to make a balance for energy of the system, which includes most of the which includes all forms of the energy, majority of the energy, because let us say electrical energy, energy associated with the reaction and or energy associated with the electromagnetic potential, etc., those terms may be added up in the right hand side of the equation. So, then we are not going to include them in a kind of generalized equation of conservation for energy, because we are developing a kind of a generalized equation not specific to any problem, any one particular problem. Okay. However, what we are going to have, we are going to have a kind of a simplification where we can use this equation for any specific problem as well. So, which we are going to see in subsequent lectures. So, when it comes to the conservation of energy, what we do, we consider a stationary volume element which is fixed in space and through which a fluid is flowing. So, that because we should also able to include the convective transport. So, that is the reason we are taking the fluid element volume element in a moving fluid, and then that volume element is fixed in space, right. So, that is the reason we are considering a stationary volume element fixed in space through which the fluid is moving. So, that a generalized energy equation can be developed. Then kinetic energy and internal energy may be entering and then leaving the system by convective transport, and there may be energy entering and leaving the system by heat conduction, and there may be work done on a moving fluid by stresses, something like because of the molecular stresses, that is like work done because of the pressure, or work done due to the pressure, or the work done because of the viscous forces, etc. Those terms may also be included, as already mentioned. And then there may be work done on system by virtue of external forces. So, external forces we are taking only gravity as of now. Let us suppose if you have additional terms like energy associated with a reaction, or energy because of the electromagnetic potential, etc. So, those terms may be added up in the right hand side of the balance equation that we are going to develop. Okay. So, but here now as external force we are taking only gravity only, because there is one reason for this. So, when we include the gravity or the work done on the system by virtue of the gravity, so then that will also take care whatever the potential energy part is there. So, that is the reason we are taking only the gravity as the part, because we have to if we are developing a equation conservation of energy equation, then we should also include the not only kinetic energy, and then we should include not only the kinetic energy and internal energy, but also we should include the potential energy, right. So, let us say we have enlisted all these possible energy associated with a given system in a very generalized form. So, then we have also enlisted what are the modes of transport possible. So, now for a moving system, and then in that moving system in a fixed location, if you take a volume element in which the fluid is moving, for that if you make a balance equation for conservation of energy, what you will be having rate of increase of kinetic and internal energy should be balanced by the net rate of kinetic and internal energy addition by convective transport plus net rate of heat addition by molecular transport, that is by conduction, plus rate of work done on system by molecular mechanism, something like stresses, plus rate of work done on system by external force like something like gravity, right. So, now this includes almost every possible way of energy associated with a given system except the reaction. So, then that can also be added if we want as a kind of additional term in the right hand side, right. So, now this is what we are having for any specific problem you have taken if you are solving any specific problem, or you are developing a energy balance equation for a specific problem. So, then some of them may involved and some of these terms may not be involved. So, but we are developing a very generalized conservation of energy equation. So, that is the reason we are including all the terms here. Okay. Now, what we do next part of the lecture is that we write a mathematical form of each and every term that has been written in this equation number 1. What is how do you represent mathematically that left hand side term? and then how do you represent mathematically the right hand side terms, that is what we are going to do individually, and then after doing them we are substituting them here in this equation, so that we can have a generalized conservation of energy equation. Okay. So, now the definition of individual terms that we are going to see. The kinetic energy is the energy associated with the observable motion of the fluid, which is given by half rho v square, that is nothing but approximately half rho v dot v. Okay. Whereas the internal energy is the kinetic energy of the constituent molecules, in whatever the molecules constituting that fluid, whatever the moving fluid is there, that molecules, whatever the molecules are there, they may be constituting some kinetic energy. So, that internal energy of that system is nothing but the kinetic energy of constituent molecules calculated in a frame moving with velocity plus energies associated with the vibrational and rotational motion along with the intermolecular interactions of all molecules. So, all these things are included in the internal energy part. Okay. However, we are not going to write individual part, what is the contribution of vibrational energy in the internal energy, what is the contribution of the rotational motion in the internal energy, what is the contribution of intermolecular interactions in the internal energy part. All those individual things we are not going to see anyway, right. So, let us not worry about that part. So, now we are not writing that potential energy explicitly in the conservation equation number 1 that we have written in the previous slide, because we are preferring to consider the work done on the system by gravity, which will also take care of the potential energy part. Subsequently, we are going to see in coming slides, right. In addition, in most of the chemical engineering problems, viscous dissipation or viscous heating a kind of important physical process, right. So, then that should also be included, but that also we have not written separately in equation number 1. Why? Because viscous heating part has already been taken care in the term rate of work done on system by molecular mechanism. How it is taken care, that we are going to do when we write a mathematical form of these individual terms of equation number 1. Okay. Further, any additional energy source terms like due to because of the chemical, electrical and then nuclear sources, they all can be added in the RHS of the equation number 1. Okay. So, now what we are going to do, we are defining a energy vector E, which includes first 3 terms in RHS of equation number 1. What are the first 3 terms in the RHS of equation number 1? Are, that is, except the work done due to the external forces, that is except the terms which are having gravity, reaction, etc., all other terms in the RHS of equation number 1 should be added or together, and then we have written them as a kind of vector E. So, that is whatever the internal energy plus kinetic energy, that part, right, or whatever the net rate of heat addition, net rate of addition of internal energy and then kinetic energy because of the convection, that part, plus net rate of heat addition because of conduction, then rate of work done because of the molecular transport mechanisms, something like molecular stresses. These are the 3 terms. All these 3 terms are now included here. Okay. So, why are we writing? Because we are going to do a balance. When we are doing going to do a balance, if you have 3 dimensional, like all 3 directions we are considering the balance. So, then what happens? Let us say if you take the conduction, whatever the rate of heat in at x because of the conduction, and then whatever the rate of heat out at x plus delta x because of the conduction. Likewise, rate of heat in at x because of the convection. Similarly, rate of heat out at x plus delta x because of the convection. Like that, if you write individual terms, there may be so many terms, and then that balance equation will become very clumsy. So, that is the reason what we are writing. We are defining a energy vector which includes all these 3 contributions: the conduction, the molecular stresses or the energy associated with the molecular stresses, and then internal energy, and then kinetic energy. All these parts we have added together and then defined our energy vector. So that we write energy, whatever the energy entering at x, whatever the energy leaving at x plus delta x, like that we write a balance and then do the simplification. Right. After doing that simplified equation in terms of E, then what we do, we substitute this equation further to expand, so that all these terms will appear in that equation. It will be a very easy process, or simpler process, rather writing individual terms, entering in, leaving out in all three directions. That becomes very complicated, and then so many terms would be there. If you miss out any term, and then anywhere in place of plus or minus, plus if you write minus, or in place of minus plus if you write, so things may become very complicated and confusing. So then that is the reason we can have a energy vector defined like this. Okay. Now here this pi dot v, that because of the viscous stresses or molecular stresses, that we already know that it is having 9 components. So those 9 components, individually you can write 3 components combination, that is pi x dot v Kronecker delta x plus pi y dot v Kronecker delta y, and then pi z dot v Kronecker delta z. Right. This is how we can have this pi dot v. Then again individual pi x dot v, pi y dot v, pi z dot v we can write as like this. So that we have all 9 components, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this particular term is having all 9 components. Now imagine these 9 components you are writing in all 3 direction, leaving, entering and leaving, so many terms will become very complicated. Okay. Further we also know that this molecular stresses, total molecular stress tensor pi whatever is there, that is having 2 contributions, 2 parts, that is tau and then p Kronecker delta, right. So that is if I is equals to j, then Kronecker delta ij is equals to 1. If I is not equals to j, then Kronecker delta ij is equals to 0, and then this part is nothing but the viscous stress. Okay. So now what we do, we substitute this pi is equals to p Kronecker delta plus tau in this equation number 2, so that we can have, in place of pi dot v we can write pv plus tau dot v, we can write pv plus tau dot v we can write. Okay. So that when you do this one, so in place of this is equation number 2, in place of pi v, if you write pv plus tau v, so then what we have, so these 2 terms are there, right. So what we are going to do is some kind of rearrangement. So then what we do, this rho u v and then this p v, okay, we combine together, we write as a one term, right, and then remaining terms like tau dot v and then q, these things are separately we are going to write as a kind of one term. Okay. So now here from rho u v plus p v, what I am trying to do, I separated out v which is common, and then from rho u tilde and then p terms I am taking rho common. So then u tilde plus p by rho I am going to have, and then 1 by rho I can write v by v tilde. So this u tilde and then v tilde are nothing but the internal energy per unit mass and then volume of the system per unit mass. So u plus pv we can write it as h tilde, so that is enthalpy per unit mass, that is what we can write. So that this equation number 2, after combining with equation number 4, we get this equation. In place of rho u v plus p v, we can write rho h v. So that is this part, that is rho h tilde v, and then remaining terms tau dot v, q, and then half rho v square v are as it is. Okay. So in a balance equation, after doing the simplification, we have not written the balance, cell balance equation we have not written. So after writing that cell balance equation, for in place of E, we can use either this equation or we may use this equation subsequently, where here u tilde, v tilde and h tilde are nothing but internal energy, volume and enthalpy of the system per unit mass. Now, what we are going to do, converting equation 1 in mathematical form. In the first part, in the left hand side of equation number 1, what we have, a rate of increase of kinetic plus internal energy within volume element delta x, delta y, delta z. So, that if you write, that is nothing but dou by dou t of half rho v square plus rho u tilde multiplied by delta x, delta y, delta z. Here U tilde is internal energy per unit mass, sometimes it is also referred as the specific internal energy, and then rho U tilde is nothing but internal energy per unit volume, whereas the half rho v square which is nothing but when you expand half rho Vx square plus Vy square plus Vz square, which is nothing but the kinetic energy per unit volume. So, all these quantities we are writing per unit volume. Remember V, this is vector V. Many times it is clearly written as specifically like a vector kind of thing, right. So, if it is not written, so then it is explicitly, that means V standing for the V vector here. Now, what we do, we take this control volume, like in derivation of equation of continuity and then equation of motion that we have done. So, we have taken a control volume of size delta x, delta y, delta z. So, the same we have taken here. So, let us say horizontal direction is x direction, vertical direction is z direction, and the third direction is the y direction. So, now in the horizontal direction at x location, the control volume is having delta x size multiplied by delta y multiplied by delta z. Okay, that is the size of the control volume. So, in the x direction, the size of the control this face is the size of the face is nothing but delta x, right. So, now at x location, at x is equals to x, whatever the energy that is entering by all means like by convection and then molecular transport is nothing but E x entering at x multiply by the area of the face through which it is entering. Area of the face through which it is entering is nothing but, this is nothing but delta z, and then this is nothing but delta y. So, that is delta z, delta y. So, in the x direction at location x plus delta x, how much energy is leaving out, or the rate of energy leaving out at x plus delta x is nothing but E x at x plus delta x multiplied by the area of the face through which it is leaving, that is delta z, delta y. Likewise, in the z direction, if you take the energy that is entering at z is nothing but E z at z multiplied by the area of the face through which it is entering, that is delta x multiplied by delta y. And then energy that is leaving at location z plus delta z is nothing but E z at z plus delta z multiplied by the area of the face through which it is leaving, that is nothing but, this is delta z, this is delta y, that is, this is delta x, this is delta y. So, that is delta x, delta y. Likewise, in the y direction also we can write. So, that is amount of energy enters and leaves across the faces of delta x, delta y, delta z control volume in all three directions. If you write E x at x minus E x at x plus delta x multiplied by delta y, delta z, right, plus E y at y minus E y at y plus delta y multiplied by delta x, delta z, plus E z at z minus E z at z plus delta z multiplied by delta x, delta y. Right. So, now in the conservation equation that we have written in equation number 1, left hand side term we have written, that is equation number 6 in the previous equation, that is dou by dou t of half rho v square plus rho u tilde delta x, delta y, delta z, that is the left hand side term. In the right hand side term, there were 4 terms we have written in equation number 1. So, that is the net rate of heat addition, net rate of addition of internal energy plus kinetic energy because of the convection, plus net rate of heat addition because of the conduction, plus rate of work done on system because of the molecular stresses. All those three terms are included in the energy vector E, and then in the form of E, that how much, what is the net rate, that we are writing here in the form of equation number 7. So, in the RHS of equation number 1, first, second, third term whatever are there, so those terms are represented by this equation number 7, and then last term in the equation number 1 is nothing but the rate of work done on fluid by external force. In the external force, here we are taking gravity, that you can get by taking the dot product of V vector and rho delta x, delta y, delta z, g vector. So, that if you do, you get rho delta x, delta y, delta z multiplied by Vx, Gx plus Vy, Gy plus Vz, Gz. So, now these equation numbers whatever 6, 7, 8 are there. So, they are representing the mathematical form of different terms that are appearing in equation number 1, that is the basic conservation energy equation. So, if we substitute this equation number 6, 7, 8 in equation number 1, then we have this equation. This part is nothing but your equation number 6, and then this part, this 3 terms, these are nothing but equation number 7, and this is nothing but equation number 8. Okay. Now, what you do, both sides you divide by delta x, delta y, delta z, and then you take limit delta x tends to 0, limit delta y tends to 0, limit delta z tends to 0. Then what you have? You have dou by dou t of half rho v square plus rho u tilde is equals to minus of dou E x by dou x plus dou E y by dou y plus dou E z by dou z plus rho V x g x plus V y g y plus V z g z, right. So, the same equation if you write in vectorial form, how you can write? You can write dou by dou t of half rho v square plus rho u tilde is equals to minus del dot E plus rho v dot g, right. So, now in this equation, this E we are going to substitute from equation number 2. From equation number 2, whatever E that we have written, because this E includes 3 terms, right. Rate of addition of internal energy and kinetic energy because of the convection, and then net rate of heat addition by conduction, and then rate of work done on the system by molecular stresses. All 3 terms are there in this E. So, those 3 terms we have written in the form of equation number 2. So, from equation number 2 we are going to substitute here in this equation. So, in this equation in place of E, if you substitute E is equals to E is equals to this form from equation number 2, what we will have? Left hand side as it is, right hand side minus of del dot of rho v square rho u tilde v one term, and then minus of del dot p v another term, second term, minus of del dot tau dot v is the third term, and then minus of del dot q is the fourth term. So, all 4 terms 1, 2, 3, 4 terms have come into the picture in the form of del dot as a kind of dot product, and then whatever last term rho v dot g is as it is, right. So, now what this term indicates? This term indicates rate of increase of energy per unit volume. What is this term indicates? This term indicates rate of addition of energy per unit volume by convection. What is this term indicates? This term indicates rate of addition of energy per unit volume by conduction, and then this term indicates rate of work done on fluid per unit volume by pressure forces, and then this term indicates rate of work done on fluid per unit volume by viscous stresses. Last term is nothing but rate of work done on fluid per unit volume by external forces, right. So, now you can see this equation whatever is there, the energy we are writing per unit volume, everything per unit volume, okay. That should be carefully observed, okay, fine. So, now this above equation we can also include the potential energy, because if you include the potential energy part, then only it will become like complete conservation of energy equation, right, because now only the kinetic energy and internal energy have been included here, but the potential energy has not been included. So, but that is already included actually, it is not explicitly shown, that is already included here, in the form of this external force by gravity. So, now what we do, we are going to simplify this term further, so that the potential energy will also come into the picture. So, what we do, let us say if g bar is minus Kronecker delta z, g is a vector of magnitude g in the negative z direction, then this potential energy per unit mass phi, we can write it as gz. That means, we can write g is equals to minus del phi tilde, this tilde indicates per unit mass, phi indicates the potential energy. So, now this in equation number 1, in place of g we are writing minus del phi and then doing some simplification. What simplification are we doing? So, in equation number rho v dot g term is there. So, here this in place of g we are writing minus del phi tilde, so that the potential energy part can also come into the final conservation energy equation. Okay. So, that now we have, so the rho of v dot g we can write minus rho v dot del phi, this is how we can write. So, now what we do, we take a vector identity formula, that is del dot SV, that is the dot product of del and then multiplication of a vector scalar. So, then we can represent as del S dot V plus S del dot V, this is how we can write. So, let S is equals to phi tilde and then V is equals to rho V, so that we can write del dot phi tilde rho V is equals to del phi tilde dot rho V plus phi tilde del dot rho V. So, now what I am trying to do? Next step, I am trying to take this term to the left hand side and then this term to the right hand side so that I can write minus of del phi tilde dot rho V is equals to minus of del dot phi tilde rho V plus phi tilde del dot rho V, this is what I can write. Okay. So, now because why I am writing, because I need this term, minus of this term is required, and now this is a dot product. So, then I can write whether it is a dot b or b dot a, it is same because it is a dot product. So, then left hand side what I am writing minus of rho v dot del phi tilde, and then right hand side it is going to be as it is like here. In this next step what I am doing, rather writing del dot phi tilde rho v, I am just writing del dot rho v phi tilde, that is what I am writing. Okay. In the next step what we have, this del dot rho v from continuity equation we can have it is nothing but minus of dou rho by dou t, that is dou rho by dou t plus del dot rho v tilde is equals to 0 from equation of continuity that we know. So, in place of del dot rho v I am writing minus dou rho by dou t, right, phi tilde is as it is. So, then in place of rho of v dot g we can write it as minus del dot rho v phi minus dou by dou t of rho phi tilde, that is what we can write. So, in equation number 11 this is what we are going to substitute. So, what is your equation number 11? So, this is your equation number 11 that we have already derived in the previous slide. So, now in place of rho of v dot g we can add these two terms minus of del dot rho v phi minus dou by dou t of rho phi, right. So, this what I am doing, this dou by dou t of this term, these two terms comes here in place of rho of v dot g. Out of these two terms minus dou by dou t of rho phi tilde I am taking to the left hand side, so that can be added along with the kinetic energy and then internal energy. Okay. And whereas this part is there, whatever del dot rho v phi, that I am adding to the first term of the first term in the RHS of this equation number 11. So, then what I can have, dou by dou t of half rho v square plus rho u tilde plus rho phi tilde is equals to minus of del dot of rho v square rho u tilde plus rho phi tilde v minus remaining terms 3 terms as it is, that is minus del dot q minus del dot pv minus del dot tau dot v, right. So, now all 3 forms of energy are coming into the picture: internal energy, kinetic energy and potential energy. So, this is the final general form of energy equation. So, if you are asked what is the energy equation, so this is what you have to write, because it is generalized equation, right. So, now what we see, it is in the form of potential energy, kinetic energy and internal energy, and then rate of heat addition or any work done on the system, etc. Those additional terms are there, right. So, the problem is that it is not in final usable form. The equation, any equation mathematical form of any physical system should be such a way that it should be in a measurable quantity, or it should be in measurable property form. That is how it should be. Okay. So, but you can measure temperature, pressure, concentration, density, etc. directly of a system without any difficulty. But if you wanted to measure internal energy, potential energy, kinetic energy, then you have to use some of these measurable quantities, either temperature, pressure, density, viscosity, velocity, etc. and then you calculate these things. So, it becomes very lengthy process. So, then what we try to do now, this equation we further simplify. How do we simplify? We now included all the terms in the energy, like internal energy, potential energy and kinetic energy. Now, we are going to simplify this equation so that we can have a equation of change for enthalpy, equation of change for internal energy, equation of change for enthalpy, and then equation of change for temperature. The equation of change for temperature, that form is going to be final usable form, easy form for the engineering applications. So, that is what we are going to do. How are we going to do? First, we are going to write a equation for internal energy. So, for that what you have to do, from this equation number 1, so you subtract the equation of change for kinetic energy, that is possible. If you use equation number 11, if you use equation number 12, from this equation if you subtract the equation of change for kinetic energy plus potential energy, then the only term would be remaining is equation of change for internal energy. So, either of 2 ways we can do. So, then what we are going to do, we are going to make use of this equation number 11, and then from this equation number 11 we are going to subtract equation of change for kinetic energy. So, that equation of change for kinetic energy that takes into consideration all mechanical aspects of the in the motion, whatever the because of the motion, because of the mechanical aspects, whatever the energy is there, that part is nothing but this one, right. So, this you can obtain by dot product of velocity vector with equation of motion and then followed by some rearrangement. So, then what you get, this one you get. So, this is we are not going to do, we are just adopting it. This how you get equation of motion, whatever we have derived in the previous lecture, that equation of motion you take, and then velocity vector u and then you take velocity vector v, you do the dot product of these two and then do some simpler but lengthier rearrangement, you get this equation. Okay. This equation indicates nothing but the equation of change for kinetic energy. So, now we are writing this equation as equation number 13. Equation number 11, already we are having this one. So, then what we are going to do? We are going to subtract equation number 13 from equation number 11, so that similar terms may be cancelled out, and then finally you have an equation of change for internal energy. So, here that if you do, then this half rho v square, this half rho v square may be cancelled out. From here also half rho v square v, half rho v square v of del dot half rho v square v, del dot half rho v square are same. So, then they will be cancelled out. Del dot q is already there. So, minus del dot pv here, and then minus del dot pv here also there, and then minus del dot tau dot v is here, and then minus del dot tau dot v is here also, and then rho v dot g here also. So, then it will be cancelled out. So, then remaining terms in the left hand side you have dou by dou t of rho u tilde only. Right hand side you have minus of this term, then plus of this term, and then plus of this term, right. So, that you write dou by dou t of rho u tilde is equals to minus of del dot rho u tilde v, this term is also there, minus del dot q, and then here minus of minus plus is there, and then minus of this term is minus p del dot v, and then here also minus of minus plus. So, then plus, but minus of this entire term is minus tau dot del v. This term is nothing but it indicates the viscous dissipation. So, the finally equation of change for internal energy, you get this equation. So, now this particular part, if you take to the left hand side, so and then added up with the dou by dou t of rho u tilde, then you can make use of a substantial time derivative, and then you can write this equation as rho capital D u tilde by dt is equals to minus del dot q minus p del dot v minus tau double dot del v. Okay. So, this is nothing but equation of change for internal energy. Okay. So, initially we have written for equation of change including all three energies, internal energy, potential energy and kinetic energy. Now, we are writing equation of change only for internal energy. This is what we have derived. Now, we further simplify this equation so that we can write the same equation for equation of change in the form of enthalpy. So, that is we are going to derive equation of change for enthalpy of the system. So, that we can get. So, this tau dot tau double dot del v whatever is there, this indicates the viscous dissipation part, and then it is having 9 terms. It is not 1 term, it is having 9 terms, and in all those 9 terms in a vectorial form, in vector summation form, it is represented it here like here. It indicates the sum of order of quantities like vectors and tensors being multiplied. So, all those terms are here. So, then when you expand these terms, you will get 9 terms that are available in any standard textbooks. We do not need to worry about them as of now. Now, switching from internal energy to enthalpy. So, we know that U is equals to H minus PV or H is equals to U plus PV. So, that U is equals to H minus PV, V tilde we can write 1 by rho, V tilde we can write 1 by rho. So, equation 14 what you have, rho of capital du tilde by dt is equals to right hand side this term as it is. So, now in place of u tilde you are going to write H tilde minus P by rho. So, that is what you are having. So, that means you are going to do substantial time derivative of H tilde minus P by rho. Substantial time derivative has to be done similar way as the total derivative being done in general. So, that is what we are going to do in several times in the subsequent slides also. So, when you do this one, what you get, rho capital D H tilde divided by dt minus rho d by dt of P by rho. So, this if you further do the substantial time derivative, then what you have, rho dP by dt minus P d rho by dt divided by rho square, and then right hand side terms are as it is. So, that means this we multiply this rho also if you bring inside. So, rho square and then this rho square will be cancelled out, and then here you have plus P rho d rho by dt, that is what we are having. So, rho dH tilde by dt minus dP by dt plus P by rho d rho by dt is equals to right hand side terms as it is. We are not doing any changes in the right hand side term. Now, from equation of continuity we can write capital d rho by dt is nothing but minus of minus rho del dot v. This is what we can write. This we have derived in the last class. So, that if you substitute here, so P by rho minus rho del dot v. So, this rho is cancelled out. So, that you can write minus P del dot v here, rest all other terms as it is. So, that this minus P del dot v in the left hand side and this minus P del dot v in the right hand side can be cancelled out, and then this minus dP by dt if you bring to the right hand side, then you have rho capital DH tilde by dt is equals to minus del dot q minus tau double dot del v plus dp by dt, and this is nothing but equation of change for enthalpy in an element of fluid moving with fluid velocity. Okay. So, now we got equation of change for enthalpy. Now, what we do, this enthalpy we write in the form of temperature, pressure, and then we try to write the equation of change for temperature. That is what we are going to do now. How are we going to do? We have to make use this relation, that is delta H tilde is equals to Cp tilde delta T plus V tilde minus T dou V tilde by dou T at constant pressure multiplied by delta P. This equation we have to make use. Okay. Now, here this equation both sides, first what you do the substantial time derivative and then multiply both sides by rho. So, then you have left hand side rho d H tilde by dt is equals to rho Cp tilde dt by dt plus rho multiplied by V tilde minus T dou by dou T of V tilde I am writing 1 by rho and then capital dP by dt, that is what we are having, right. So, now this left hand side as it is, right hand side first term is as it is, this term here again what I am writing V tilde again I am writing as 1 by rho. So, now this whatever you multiply inside this rho, if you bring in, so what you are going to have? You are going to have 1 minus T rho and then dou by dou T of rho at constant P. So, then then we have rho square, rho multiplied by 0 minus 1 and then dou rho by dou T, that is what you are going to have. So, then that we can write 1 minus T rho and this is minus 1 by rho square dou rho by dou T. So, that I can write 1 plus T by rho dou rho by dou T. So, T by rho dou rho by dou T I can write dou rho by rho divided by dou T by T. So, that I can write dou ln rho by dou ln T. So, that is 1 plus dou ln rho by dou ln T I can get, that is at constant pressure. Remaining terms are as it is, right. That means rho dH tilde by dt is equals to rho Cp tilde dt by dt plus dP by dt plus dou ln rho by dou ln T dP by dt. This capital D by capital DT indicates substantial time derivative as we have seen in the previous lecture, right. So, now what we do, this part we are going to substitute in equation number 14. This equation number 16 whatever we just derived, that we are going to substitute in equation number 15. Okay. So, in place of rho dH by dt we are going to write this part from equation number 16. So, that you have this equation, right. So, now here left hand side capital dP by dt and then right hand side capital dP by dt can be cancelled out, and then left hand side we keep only this this term and then whatever the dou ln rho by dou ln T term is there, that we take to the right hand side. So, that rho Cp tilde capital dt by dt is equals to minus del dot q minus tau double dot del v minus dou ln rho by dou ln T at constant P, this is important, multiplied by dP by dt, right. So, this is nothing but equation of change for temperature. So, now here this term indicates the rate of increase of temperature, the temporal term, and then it also includes the rate of addition of temperature because of the convection. This term indicates the rate of addition of temperature because of the conduction. This term indicates rate of addition of temperature because of the viscous dissipation, and then this part indicates the rate of addition of temperature because of the work done because of the pressure forces, all those terms are included, right. But in general we do not use this entire equation in the complete form, right. So, now this is the final energy equation in the form of temperature, right. So, all these equations of change whatever we have seen, they are energy equations only. First equation is that including all three forms of energy, that is kinetic energy, potential energy and internal energy. Then we have written for the separately internal energy, then separately for enthalpy, then now separately for in the form of temperature. So, it is different forms simplified one after other, we are reducing the complexities and then finally come to one form of equation where the terms are having something which are measurable. Right. If at all if you wanted to do the validation with experimental parts, so it should be in a measurable term. So, that is temperature, density, velocity, all these things are measurable. So, that is the advantage of this form of equation of change for energy, okay, for non-isothermal systems. So, now here minus del dot q is nothing but del dot k del t, right, and then minus tau double dot del v is nothing but mu phi v plus kappa psi v. Here for Newtonian fluids, this part whatever is there, that can be written as this equation. Here k is the dilational viscosity and then mu is the viscosity. If the Kronecker delta if I is equals to j, then Kronecker delta I j is equals to 1. If I is not equals to j, then Kronecker delta I j is equals to 0 in this equation, right. So, this term indicates degradation of mechanical energy into thermal energy, which is known as the viscous dissipation heating or energy due to the viscous dissipation. Okay. And this usually have the importance when we have high viscous fluids which are moving at high velocity. Usually high viscous fluids does not move at high velocities in general. So, then in most of the application the contribution of this viscous dissipation is very small. However, there are many cases it is also included. Okay. So, now what we do, we take a case where the conductivity is constant and then where we take the case the viscous dissipation heating is negligible. So, when we take those assumptions, then this equation number 17 we can write in this form, that is rho Cp tilde capital dt by dt is equals to k del square t minus dou ln rho by dou ln t at constant p multiplied by dp by dt. Okay. This is even further simplified compared to the our previous equation number 17, because now we have taken in Fourier's law k is constant and then viscous dissipation terms we have neglected. Now, we take a few further simplifications of these equations. So, what we do, we take a ideal gas, for ideal gas Pm is equals to rho R T at constant pressure. What if we rearrange this equation, Pm by R is equals to T rho, and then if you take the differentiation both sides, in the left hand side m is constant for a given system, R is constant, P is also constant because we are doing at constant pressure. So, left hand side is equals to 0 and right hand side term we have rho dt plus T d rho. So, that if you simplify you get dou ln rho by dou ln T at constant P is nothing but minus 1. Okay. So, this if you substitute in equation number 20 here, so then what we have, rho Cp tilde capital dt by dt is equals to k del square t plus dp by dt. This is what we are having. Now, for the same ideal gas, what we have, Cp minus Cv is equals to R. Both sides if you divide by molecular weight of the gas whatever you have taken, then you have Cp tilde minus Cv tilde is equals to R by m, because this tilde indicate per unit mass. So, that Cp tilde is equals to Cv tilde plus R by m we can write. So, what are we going to do now here? The previous equation we have written in terms of Cp tilde, now we are going to write in terms of Cv tilde. Further then rho Cp this equation from here as per this making use of this relation, what we can write, rho Cp tilde capital dt by dt is equals to rho Cv tilde capital dt by dt plus rho R by m capital dt by dt. That is nothing but this equation we are multiplying by rho and then multiplying by capital dt by dt both sides. Now, in equation number 21, wherever rho Cp tilde dt by dt is there, you make use of this particular thing here, so that you get the equation in terms of Cv tilde. Okay. So, that is rho Cv tilde dt by dt is equals to k del square t plus dp by dt as it is. Whatever rho r by m capital dt by dt is there, that we are taking to the right hand side. So, then we are getting minus rho r by m capital dt by dt, right. So, further we have Pm is equals to rho RT for the same ideal gas, that we can write P is equals to R by M T rho. Why are we doing here? Because we wanted to just get rid of these additional terms here in the right hand side. So, now this equation, if you do substantial time derivative both sides, capital dP by dt is equals to R by M T capital d rho by dt plus rho capital dt by dt, that is what you get. So, in place of dP by dt, here in this equation number 21, you substitute this expression here. So, that you do rho Cv tilde dt by dt is equals to k del square t as it is, and then R t by m d rho by dt plus rho r by m dt by dt, and then minus rho r by m dt by dt of equation number 22 as it is. So, this term you can cancel out, because one is plus and another one is the minus. Then further from the continuity equation, in place of capital d rho by dt, you can write it as minus of rho del dot v, and then for same ideal gas RT by m, we can write P by rho. So, in place of RT by m, I have written P by rho here, and then in place of capital D rho by dt, I have written minus rho del dot v for this part. So, that this rho and then this rho is further cancelled out, and then we have this equation rho Cv tilde capital dt by dt is equals to k del square t minus p del dot v. This is what we have, right. So, the same equation in different forms in different variables we are writing, that is it. So, as a summary, what we have in terms of temperature, equation of change for temperature, we have this equation, we also have this equation for ideal gas system, and then we also have in terms of Cv tilde this equation. These are the things just now we have derived. Okay. These are some special forms. We are writing the same equation for different cases. Okay. So, this is all we have written for different cases. Now, let us say if you have a fluid flowing with constant pressure, if the pressure is constant, then capital dP by dt is going to be 0. So, this equation here, if you write capital dP by dt is equals to 0, then you have only rho Cp dt by dt is equals to k del square t. Then if you have a fluid with constant density, then again dou ln rho by dou ln t at constant p is equals to 0. So, this part is 0 anyway. Then again we have rho Cp tilde capital dt by dt is equals to k del square t. Remember, this equation is the general equation. This is not for a ideal gas. These are for ideal gas, but this is not for ideal gas. This is general any fluid, right. So, now finally, for a stationary solid, if the solid is there, that is the fluid is not moving, or if you have a stationary solid, then vector v is 0. Then in the left hand side, rho Cp tilde in place of partial in place of substantial time derivative, you have to write a partial time derivative, because substantial derivative, in the substantial derivative, if the v is 0, that is nothing but the partial derivative, you get only partial derivative term, right. So, these are the equation. So, this equation if we expand, then we have rho Cp tilde multiplied by dou t by dou t plus Vx dou t by dou x plus Vy dou t by dou y plus Vz dou t by dou z is equals to k dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square, this is what we have in Cartesian coordinates. Likewise, we can have the equation in cylindrical and spherical coordinates. Okay. So, now we have seen basics of transport phenomena part also, the derivation of continuity equation, momentum equation and energy equation. And then previously we have seen so many details of non-Newtonian fluids. So, from next class onwards, what we are going to see? We are going to see a few problems associated with the transport phenomena of non-Newtonian fluids. Okay. The reference for this lecture, the entire lecture is prepared from this standard textbook, Bird, Stewart and Lightfoot, that is Transport Phenomena 2nd edition, but similar details may also be found in these two books, that is Dean and then Panton. Additional reference may be available in these two books as well. Thank you.